Hi, welcome to SUSECON Digital 2020. This session is SAP High Availability in Azure using SUSE Linux. And my name is Ross Sponholz. I am from Microsoft working with SAP in Azure exclusively. And Stephen?
Yeah, my name's Stephen Mogg. I work in the pre-sales team over in EMEA looking after SAP and public cloud.
All right, so let's jump into this. The agenda today, we're going to talk about basic SAP architecture, SAP high availability architecture in Azure, pacemaker, SUSE clustering, and then talk about the Azure load balancer and how that comes into play. So starting off with the SAP architecture. Now this slide is just a basic view of SAP architecture, very simplified. So starting out at the bottom, we have database storage. SAP stores all of its data in the database for the most part, and then we have a database server, of course, that is providing queryability, that kind of thing. That's generally either something like Oracle, SQL Server, or in more recent times, HANA database from SAP. And then we have an application server that has the actual business logic that is running the SAP applications. Clients up above there talk to the application server. Now, there are a couple of other components that are what we call central services. That's really a queuing and locking mechanism so that your multitude of application servers don't conflict with each other and get inconsistent data. And they use a shared disk infrastructure, typically NFS, and those all work together. Now, for high availability, I've put the yellow star on the database server, shared disk, and central services because those in an SAP architecture could potentially be single points of failure. So if we only have a single instance of our database, if that goes down, then the system is down and not operational. So what we have to do is for high availability, have protections for that, those components to be a highly available environment. So moving on into how we actually implement those things in Azure, this is a picture of the S/4HANA high availability architecture. Also, we know this is the Microsoft or SAP reference architecture. So we recommend that most of our customers start out with this type of an architecture. So starting over here at the left-hand side, very similar to what we just saw, the database over on the right-hand side, and generally we'll try and implement that in a high availability mode so that we have a primary and a failover. If there's any problem, we can fail the database over to the replica and be able to be back online and not really interrupt any operations. Similarly with the central services here in the middle, we have the ability to have two instances, one that's called the ASCS, the other one the ERS, or the NQ replication service. And if there's an interruption to the primary, we can fail over to the replica and continue running. And the same situation with the NFS capabilities. So fundamentally, what we're doing is using more servers to be able to fail over to the standby server if there is any problem with the application or the infrastructure, whatnot, and continue to give a highly available experience to the end user. So some of the features, we're going to go into quite a bit of detail about how this actually works. But starting off with one of the, or two of the Azure features that we generally make use of for high availability. On the left-hand side is availability sets. And those are a Azure construct that essentially tells Azure not to deploy machines that are in an availability set to the same hardware. And in fact, what we'll do is put them in different racks in our data center. We'll make sure that any kind of updates happen so that they don't affect all of the machines in an availability set at the same time. So that gives you a level of availability inherently, because then the machines aren't on the same host, and they're not going to be updated at the same time. Then more recently, we've come out with what we call availability zones, and those are really collections of data centers in a given Azure region. And so the availability zones, we generally structure having 3 availability zones in a region, and those zones do not share any common infrastructure. So, for example, they won't have a common power feed. That they'll have their own power feeds, and they don't have a common network connectivity. They'll each have their own. So that really protects against those infrastructure issues that might come about. Now, availability zones and availability sets are mutually exclusive, so you have to choose one or the other that you're going to work with, which the availability zones, if you can use them, should achieve a higher availability overall. Now, one caveat that I'd like to throw out with regards to availability zones is that we have to do some testing. We have variability in the physical layout of the regions for Azure. So what we need to do is go check the latency between the availability zones and really do a measurement there. And we have some scripts that'll do that for you, and we can point you to that as one of the resources at the end of the presentation. So the end result is some of our regions have very low latency between them. Some of them are more geographically dispersed. You really want to know that as a customer and deploy things appropriately. All right, Stephen.
Thanks, Ross. So what I'd like to do is just tell you a little bit about the SUSE High Availability Extension. So we've just seen some of the capability in Azure to help provide that resilient SAP infrastructure. But it's important to note that the SUSE HA extension won't improve on the SLAs you've seen there, but what it will do is reduce the time to recovery in the unlikely event that your VM fails inside Azure. Now, the actual SUSE stack itself is quite simply, when we talk about the HA stack in Azure, we're normally talking about a Linux cluster. And you can see that represented here by this stack. We've got a pair of Linux VMs with some storage attached to provide what's called an SPD, and we'll cover that a little bit later in this presentation. But what we're talking about is our pacemaker stack, and on top of that sits a number of services, whether they will be SAP databases or IP addresses or various other resources which we need in order to provide that SAP infrastructure. So what I'd like to do is take you through each of these layers. So the first one is CoraSync. Now, the CoraSync is essentially our messaging and membership layer of the cluster. It doesn't know anything about SAP. All it does is its entire role is just to decide which servers are in the cluster, which are out of the cluster, and just report that through as needed. Now, most of the communication in the past has been done over multicast for on-premises solutions, but in Azure we use unicast, which means that you'll need to supply the IP address of every node in the cluster and put that into the CoraSync file that's at the bottom of the page there. So, as it says, CoraSync simply performs the cluster heartbeat, so it's constantly telling the world that it's okay, and also listening to understand if any of the other servers are up or down, or if they're a member if they're a member of the cluster. So for those that have done CoraSync and pacemaker clusters on premises before, it's important to note that there are a couple of differences when deploying this solution inside of Azure. Now, the first and obvious one is the token. Now, we set that to 30 seconds. It's essentially the timeout for the cluster. So we set that up to 30 seconds. Now, that's not unique to SUSE. So if you deploy a Windows cluster inside Azure, you'll also set the quorum timeout to around 30 seconds as well. So it's important that you make that change inside the CoraSync file. The other one that you must change from the default is the consensus. Now, the minimum setting it needs to be is about 1.2 times the size of your timeout. If it's less than your timeout, you're going to experience some very strange cluster behavior. So make sure you do change these two settings. But when CoraSync detects a failure, it obviously can't do anything about it itself because it doesn't control anything about the cluster. But what it does do is it informs the next layer up the stack, which is pacemaker. So pacemaker is essentially a policy engine. It will understand from the CoraSync layer which servers are up and down. It'll keep an eye on resources, and in the event that it needs to do a failover, it will make the decision on whether to restart a resource or fail that over to a second node in the cluster. A couple of facts in here. The actual configuration of the cluster, the pacemaker configuration, is saved in an XML file, and that's copied to all the nodes in the cluster. And the other thing is, once something is controlled by pacemaker, you shouldn't really touch it with tools outside of that, because again, you're going to experience some strange behavior with those resources. Now, pacemaker itself, again, doesn't know anything. It doesn't know how to handle an IP address or a disk subsystem or an SAP database. So it needs some intelligence on top of that. And this is what our resource agents do. Now, essentially, they're just scripts which know how to stop and start resources. And it's those that we supply which allow you to cluster up things like SAP HANA and SAP NetWeaver as well. In fact, out of the box, we actually supply something like 140 different resource agents, which cover everything from various databases through to disks, file systems, and so on. However, it's probably important to know that if you do want to do clustering inside Azure for SAP HANA and have the ability to fail over between primary and secondary nodes within SAP HANA, then you do need to deploy SLES for SAP applications, which has all the resource agents which you need to do this. So the top layer in my original diagram was fencing. And fencing is probably one of the more important parts of a cluster in times of failure. So if you can imagine, we have two cluster nodes, and the first one has all our resources, all our databases and disks and IP addresses bound to it. If there is a loss of the node, then it's quite safe for the second server to start up those resources, mount the disks, start the database, and continue processing. But what if it's just a network problem? What if the server is still okay, still responding, but for some reason the two servers in the cluster can't see each other? It's then not safe for that second server to start up the database and mount those file systems, because that's just going to lead to an awful lot of trouble. So what we're solving with fencing is our split brain issue. And that's where we need to know that it's safe for that second node to be able to start those resources without causing any trouble. So what we do is we have something called a stonith, which is the ability to shut down or kill off an original node when a node thinks it's the only one left in the cluster. And by doing that, what we're actually moving from is an unknown state where we're not sure if that first server is down or not, to a known one where it's definitely dead. And the thing is, if the server was down for legitimate reasons, then if you shoot it and it dies, it's not a problem. It was already dead. On the other side, if it's up and running and it gets killed off and your services fail over to the second node, at least you're not going to suffer any data corruption, which is the primary purpose of the cluster, is to protect the data. So we need to ensure that doesn't happen. So to take you through how we handle all this stuff inside Azure and how we deploy this, I'll hand you back over to Ross.
Okay, so let's go talk about how we implement all of this in Azure. By the way, I noticed we didn't explain the STONITH is creatively named is an acronym for shoot the other node in the head, which sounds a little bit extreme, but the whole idea is to make sure that we only have one machine that's saying that it's the active server in these scenarios. So in Azure, we have some architectural options when it comes to deploying SAP. And so let's start at the top. For the shared file system for the SAP mount, et cetera, those kinds of uses, those are connected to by all of the app servers and the central services machines. And so we can build your own, a customer can build their own SUSE cluster using the NFS and DRBD that gives you replication between multiple nodes so you, in a cluster. So you can have a highly available NFS in Azure purely using SUSE Linux virtual machines. We also have a relatively new functionality called Azure NetApp Files, and that's essentially an NFS as a service, and you can use that for database files as well as the central services SAP mount type of storage. And all you have to do there is provision volumes and then use them. So that's a nice capability. We're also extending, we're in the process right now of extending what's called Azure Files, which is the shared file system from Azure, to encompass NFS scenarios as well. So you're going to be able to use that as the shared file system for SAP. The advantage to using that is that it's very low cost, not necessarily high performance, but the costs are very low. Now moving on to the deployment, of course, we talked about availability sets and availability zones. You're going to make that determination based on the regions that you want to deploy in and your availability service level agreements to the business. And then finally, with the fencing agent, we now have two choices. The SBD, which is basically based on shared iSCSI devices that the nodes communicate through, or we now have what's called the Azure fencing agent, which is a capability where one node can shut down the other node using the Azure API. And that's provided as a fencing agent in SUSE Linux. However, the requirement there is it's SUSE Linux 15 or higher only. So if you're on a previous version, SBD is the way to go. All right, so we talked about the ability to fail over between two nodes and how the cluster can do that and control that process. But how do client machines make sure that they're talking to the right instance? Well, this is really a description of that. In a traditional on-prem environment, what we would have is what's called a floating IP address, which is the IP address is able to, let's say, be on, in this diagram, HANA 1. And as we're operating, that's fine. The primary app server, for example, talks to HANA 1. And if there's a failover necessary, the cluster can control which node is talking on that IP address. So if it fails over, the cluster controls that IP address and says HANA 2 is now the server providing that floating IP address. Well, in Azure, we don't have floating IP addresses like that for clustering because of the software-based networking. So what we have to do is use what's called the Azure Load Balancer to direct the traffic between the two machines. And I'm going to go into a little detail on how exactly that works. So fundamentally, the Azure Load Balancer directs traffic between the two nodes. So you can create a back-end pool of machines, in this case HANA 1 and HANA 2. And the load balancer has a facility called a health probe. And what it does is it checks with each machine to say, are you okay? And the machine can respond, or it can give an indication to the load balancer that it is okay. So in a SAP scenario, in a cluster scenario, what we do is we configure the load balancer health probe to just check for an open port in the back-end pool, and we allow the pacemaker cluster to use a facility it has to open the port on the active machine. So we're going to go into a little detail of exactly how this works. So starting off, that HANA 1 is going to be the primary machine, and we set up HANA system replication between the two nodes. So HANA 1 is going to be the primary, HANA 2 is the replica. Now the health probe is going to check for both of the machines' health. And what we do is make sure that with a cluster that HANA 1 is the active machine, so it's responding true. The green check mark says, yes, I'm healthy. Now, HANA 2 in that situation is going to say, nope, I'm not the primary, so don't send me any traffic. So the Azure Load Balancer will send all of the traffic from the app servers to HANA 1. And again, the health probe on HANA 2 is saying, no, I'm not the active one, don't send me any traffic. So traffic only goes to HANA 1. Now, what happens if HANA 1 fails for whatever reason? Let's say we have a hardware failure, HANA 1 goes down, the network, the pacemaker clustering software detects that on HANA 2 detects that we can't talk to HANA 1 anymore. So in the underlying software, in the resource agent, what happens is in the HANA resource agent, we tell HANA 2 to do an SR takeover. If you're familiar with HANA, that just means I used to be the secondary or replica, now takeover is the primary. And that would happen after the fencing occurred, by the way. So then we want to move the floating IP over to HANA 2 so that it gets the traffic. Now, the health probe is going to fail trying to go to HANA 1 because it's down, and even if the machine came back up again, the clustering software would say, no, I'm not the primary anymore, so don't send me any traffic. However, the health probe succeeds on the new primary machine, the HANA 2, and so then we get the traffic from the application server. So that's really how the failover works in detail. Now, a really low-level detail that we have now, and here's a lot of text that you'll probably want to sort out later on, is that we use the SoCat program. SoCat is a generalized TCP client and server application. And really, we use the SoCat program just to open up a port on the active machine. The cluster can configure which of the machines that the SoCat program is running on. So what we do here is tell the pacemaker cluster that the SoCat program must run on the same machine as the active HANA machine. And that's what can control the health probe from the Azure Load Balancer. Okay, so with that, we have a little bit of wrap up, a few takeaways. First, read the documentation. We have really good documentation, both from the SUSE perspective and the Azure perspective on setting this up. The setup can be complex, so please try and understand what you're doing with this rather than just go through the steps. There are some customizations that you have to make based on your, for example, host names and SAP SID names, those kinds of things. And what I would recommend is start with a known base configuration. After you've done that and done testing, then you can customize that configuration to make it fit your scenario better, but start with something that's known and tested. Speaking of testing, what you want to do is set this all up and then make sure that everything is working as desired. So test that failover, both a controlled movement of resources as well as a unplanned failover, for example, shutting down the active machine and watching the takeover happen. That's really important because there are a lot of configurations and you want to make sure that everything is working properly. And then after you've done that, since your requirements may be different than what we've documented, then you may want to do that customization for your own scenario. Also related to that testing is you really want to understand the operations. You want to go through the process of dealing with a planned migration of resources as well as unplanned migration, and what are the steps that you do from an administrator standpoint. And I would say document what those steps are or create shell scripts that implement those steps. That's really important, and you want to do that obviously before you're in the situation that you need those facilities. And then finally, set up monitoring and alerts. You can set up alerts in the pacemaker clusters so that, for example, if an event like a failover were to happen, you could be alerted to that, that event. You can also use Azure Log Analytics so that gets faced up through the Azure environment, and you can put alerts via email or text messages through that alerting facility. So I would say that's very important. If you think about a database, you wouldn't want it to fail over and not know that that's happened because you're then in a state that there's some administrative efforts that are needed. And then on to resources. So, so we have really good documentation, again, both from the SUSE perspective and the Microsoft perspective. We've set up high availability with SAP and in Azure, and have extremely detailed documentation. We also have created automation for deploying this out, deploying a recommended architecture for SAP and Azure. There are some really good training and certification classes. We listed the SLE 321 class, which is on it's on the high availability clustering. I took that class and it is excellent. So I would highly recommend that, and there is a certification associated with that. And then Microsoft has created the AZ120, which is administering SAP in Azure, which also is highly recommended that you at least understand the materials for that. And then over here on the right-hand side, we have some other SUSECON Digital sessions that you might want to take a look at, including the high availability with NFS, and another session for central services on the bottom, the HOL 225 hands-on lab for Azure, or sorry, not Azure, SAP NQ replication. All right, with that, I think we're going to wrap up, and thank you for joining us.
Thanks very much.